Welcome back, children. The next thing that we'll see will be the AC voltage applied to a capacitor. In the previous video, we saw AC voltage applied to a resistor and AC voltage applied to an inductor, and now we will see the AC voltage applied to a capacitor. So I have this AC source like that. Again, V is given by Vm sine omega t. So that's the voltage. That's alternating current voltage. Okay, this is going to be applied to a capacitor. Value C. So clearly, there would be a current flowing through this. Okay. So this is an electric circuit now, and unlike the DC voltage, the capacitor will not stop after charging. So what we saw in the DC voltage case was that you had it was like this. You had a battery and then you connected a capacitor to that. This is V and then this is C, and this will charge the capacitor, and once it reaches a certain charge Q, then this will stop charging, right? So there will be no current that will flow after you have charged this capacitor to a certain value, so that this voltage across the capacitor is equal to the applied voltage. If these two are equal, then no charge will flow, so current will be zero once this charging has taken place. That is what is happening in DC. But in AC, that is not the case. The voltage is constantly changing. So as it is constantly changing, then the current would also be constantly changing. So you will charge, discharge, charge, discharge, and this activity will keep on happening. So a regular current will be flowing all the time. Unlike the DC, where the current starts to flow and then stops after you have reached the applied voltage across the capacitor. Unlike this will have continuous current. Not a constant current, but a continuous current flowing in the circuit, because the voltage is changing all the time. So this voltage and this voltage, if this is greater than this will start discharging. If this is greater than this voltage, then this will start charging. So that will always happen. Okay. So what do we know? We know that in a capacitor, CV is equal to Q, okay, or V, rather, I'll say V, can take this voltage across this capacitor as VC. Okay, so let's say VC. So VC is equal to Q by C. This you know. Okay, so what else do you know? You also know that VC must be equal to V all the time, because Kirchhoff's voltage law should be obeyed. Whatever be the circuit and whatever be the time, it should be obeyed at all times. So what you would have here is that your VC will be equal to V, and that is also equal to Vm sine omega t. This should be met all the time. I mean, another way of doing it is, so I'll say like this is plus and this is minus, so you start charging, so this will be plus, this will be minus here. So if I start doing the voltage law, and I start from here and come back to the same position. So positive, negative, so I'll get VC, and then I come here, it's going to be minus V, because minus plus must be equal to 0. So VC must be equal to V at all times, and that is what we are doing here. Okay, I hope this is clear to you. Okay, fine. So what is our intent? Our intent is to find the current. Okay, the relationship between the voltage and the current. That's what we have been doing. So Vc is equal to Vm sin omega t, which means Q by C, if we take this as equation 1 and if we take this as equation 2, 1 is equal to 2. Since 1 is equal to 2, then Q by C must be equal to Vm sin omega t. Okay. Then Q can be written as C Vm sin omega t. Okay. What is current? Current is the rate of change of charge. So dq by dt would give me current at that particular point in time, right? So dq by dt is equal to I at a particular point in time, I of t. So that is equal to d by dt of C Vm sin omega t. I can take C Vm out. So I is equal to C Vm can be taken out. And if we differentiate sin omega t with respect to t, then I will get omega into cos omega t. So I can be written as omega c and then Vm cos omega t. Okay. So this is cos and this is sine. So clearly there is a 90-degree shift in it. Anyway, so we know this. What else do we know? We know this, right? We know that cos omega t or cos theta is equal to sin theta plus 90 degrees. Okay? Or cos theta is equal to sin theta plus pi by 2. So using that, what I'm going to get here? So I is equal to omega c Vm and then sin omega t plus pi by 2. Okay, so this is my current equation. At any point in time t, this is a value of the current I get. At any point in time t, this is a value of the voltage I get. Now what is the relationship? You notice that this is plus pi by 2. So what does it mean? If t is equal to 0, V will be 0. But what's the value of I? I would be this times sine of, this is 0, but this will be pi by 2, so 1. So I'll have, this I can treat as I max, right? So this I can be written as Im sine omega t plus pi by 2, where Im is equal to omega c Vm. Okay, so this is it. So if this is 0, if time is equal to 0, V will be 0, but when time is equal to 0, this would be sine pi by 2, so 1 Im. So when V is equal to 0, I will be maximum. Okay, and if this is pi by 2, then what happens here? This pi by 2 plus pi by 2, this is pi. So this will be 0. So it is like current is leading the voltage. You see what happened in the case of the inductor? The inductor, voltage was leading the current. Current was lagging behind the voltage. So first in the inductor, voltage reached its peak and then current reached its peak. Voltage became 0 and then current became 0. So current was kind of following the voltage. And here it's other way around. Here the voltage is following the current. Current reaches the maximum, after that the voltage reaches the maximum. Current reaches 0 and after that the voltage reaches 0. So that is what if you put the right values, then you will get this relationship. Okay. So the graph of that would be something similar to this. Okay. So the graph of this will be, we will draw this. Okay. Again, So this would be my voltage. Okay, this is going to be this is time, and then this axis will be voltage this way. So start from 0, we go here, and then we come here, go all the way down, go, and then we go like that. This is the voltage graph. And what is the current graph? Let's see. When this is 0, voltage is 0, when time is equal to 0, then this will be pi by 2, so it's here. Sorry, this is it. This is here. This is the current graph, okay? And when that is pi by 2, then you get what do you get here? You get this is pi by 2, it will be pi, so it will be 0. Okay? And 3 pi by 2 would be next one, 3 pi by 2. It's going to be negative, right? 180 minutes, so then you get to this. And this. So the current graph like this. So this is your current. Right. Notice here, this current reaches maximum first, and then the voltage reaches maximum. Then current reaches 0 from there first, and then voltage reaches 0. Then current reaches negative maximum first, and then voltage reaches negative maximum. See, it takes a longer time than this. This reaches its maximum before this reaches, in a shorter time than that. So you can say that the voltage is lagging the current, or the current is leading the voltage. So in the case of an inductor, current was lagging the voltage. In the case of a capacitor, the current is leading the voltage. Okay? So I want you to think about it and understand it. Take it in properly. Okay? Okay. Now let's focus on this. Im is equal to omega c V, right? Okay. So Im is equal to omega c Vm. Can you compare this with Im of the resistor? In the case of a resistor, what did we do? In the case of a resistor, we said Im was equal to Vm by R. So, and this is resistor, right? In the case of resistor. And in the case of inductance, what did we say? In the case of inductance, we said Im is equal to Vm by omega L. Okay? So this is equivalent to resistor in the case of L. And what is going to happen in the case of C? Im is equal to omega C Vm. So how can I represent this like that? Well, this is in multiplication with this stuff, but then I need a quantity with which I have to divide this to have a resistance equivalent, right? So then how can I convert that? So I can say that Im is equal to Vm by 1 by omega c. Okay, it's 1 by omega c. So omega c will go here, and this will become the first one. But now I have written this omega c into Vm in this form, so that I can say that this 1 by omega c is like my R, or this 1 by omega C is like my omega L, and this 1 by omega C will have the unit ohm. Okay, so this 1 by omega C is called as XC, which is equal to 1 by omega C, and this is called as capacitive reactance. So reactance, capacitive reactance. Okay, this is called as capacitive reactance. So here, if I have to sum it up, then I'll say capacitance, then I'll say Im is equal to Vm by 1 by omega C, and that is actually equivalent to resistance. You see, only in the case of resistance you call it as resistance. In the case of inductance, you call this omega L as reactance. This is resistance, this is reactance, and this is also reactance. Resistance and reactance. This is reactance, this is also reactance. But this reactance is due to induction, so you call this as inductive reactance. And this reactance is due to capacitor, so you say that it is capacitive reactance. But basically, it is reactance. So resistance and reactance. This is resistance, this is reactance, and this is also reactance. This is inductive reactance, and this is capacitive reactance. I want you to get this clearly. So both of them will have the same unit, ohms. Okay, one is resistance, and the other one is called reactance. When they combine, then you will still call it as reactance. Okay? When you have a circuit where you have capacitance and also inductance, then you will call the net. You will have a net reactance. Okay, but that's different. So I hope this is clear to you. And what about power? How do you calculate power? Okay. So that is something that we will see now. So let's do the power calculations now. Okay. So what is power? Yeah, you have two things: instantaneous power and average power. So instantaneous power at any instant, P of t, is given by V at that time t and I at that time t. Okay, so what is V at a particular time t? That is Vm sine omega t. And what about I of t? So what happened to that? What was your I? Your I was actually, we just saw that this was omega c Vm Im, right? This is Im cos omega t. Cos omega, or sin omega t plus pi by 2. So this is what you have. So when you bring them all, when you group these things together, then you can get omega c, then Vm squared, and then sin omega t cos omega t. Okay? Again, so this has certain pattern, you can see that. Okay, so I can multiply this by 2 and divide it by 2. Then if you do that, then I have omega c Vm squared by 2, and then 2 sin omega t cos omega t. But what is 2 sin omega t cos omega t? It's 2 sin theta cos theta. So that will be sin 2 theta. So I get omega c Vm squared by 2, and then sin 2 omega t. And that's my Pt. This is my instantaneous power. Power at any particular point in time. So if I know the value of t, and then omega c and Vm squared, then I can easily calculate what power is consumed or given, depending on whether it's positive or negative, by the circuit. Okay, so I can do that using this at any particular point in time. But then we are not going to be happy with that situation. We are going to find the average power. On the average, how much power is consumed over time. Okay. So for that, we find the average power over one cycle. If we can find the average power over one cycle, and that must be the same for the second cycle, third cycle, fourth cycle, so you can get one particular number throughout, right, for all times. So that is what we are trying to do here. So the average power average is equal to, we are going to take P of t dt, we are going to integrate it over one full cycle, and then I will divide it by the time period of the cycle. So if I do that, then I get the average power. Okay, so that is going to give me 1 by t time period, and omega c Vm squared by 2. I am taking this constant, I am taking it out of integration. Okay, so effectively then I get 0 to t sine 2 omega t dt. So P of t, I've just done all of that in just one step. Okay, you can probably do it in one more step, but that's okay. So you know the value of this, right? So sine 2 omega t dt over one full cycle. The average value of a sine function over one full cycle is 0. So this term will become 0. If this becomes 0, this is going to be equal to 0. If this is 0, everything else will be 0. So the average power is equal to 0. Okay? So what you need to understand is that both in the inductive circuit, the pure inductor, and in the capacitor circuit, the pure capacitor circuit, okay, in both circuits, the average power is 0. So these circuits do not consume net power, but a resistor will always consume power. I squared R losses will always be there. But in the case of a capacitor or an inductor, the average power is at some instant, they may consume power, but then they hold that power and then give it back to the source later. Okay, so on the average, they won't consume any power. It's like this. You may be getting some amount of money from your father, so you are the resistor, right? So if the father is giving you, the child, the money, okay, so the child spends that money all the time. It needs it for chocolates or whatever, wants to go to a movie and spend the money with friends, and it does that, the child does that. But that is like resistor, okay, the child is like resistor. The inductor or a capacitor, okay, the reactance is like something like this. It is like your father giving somebody a loan, okay, so that loan will come back to your father. So on the average, there is no net money given to a neighbor. So the guy wants 1,000 rupees, urgently for some purpose. So you give the money to your father, gives that money to your neighbor, and then he gives the money back to your father tomorrow morning. Okay, he needs it urgently now, and then he gives it back to your father tomorrow morning. So the net money transaction is 0. So reactance is like that. Reactance is like your neighbor to whom your father gives money. Resistance is like you to whom your father gives money, but that never comes back. Okay, so power is like that. Okay, so I can also done that mathematically. I can show that to you graphically as I did in the case of the inductor. Okay, so for that I'll have this graph. Okay. Value voltage is going to be power, right? So this will be current, voltage, power. Okay, so as usual, this is voltage Vm maximum, and I'm going to use different colors, right? So this is going to be my I max, okay, and this would be my P max. Okay, three different colors I'm going to use now. So what's my voltage going to be? So I'm going to start from here, right? So this is my time in this direction, and all these things are upwards. Okay, voltage, power, current, they're all involved. I would mark all of them in one graph. So I'll start with the voltage. So I start here, then 0, sine curve, like that, like that. Like that. Okay, so this is my voltage, maybe. And what is my current? Okay, so this has to be like this, right? So this should reach peak first, and after that should reach. Okay, so this is the current sine wave. Okay, so this is my current. Then, as you can see, in this bit, okay, Im is here, I is here, V is 0, so this will be 0 clearly. And here, as you come here, this is maximum, this is 0, so this will be 0 here. And so it starts from 0. And in this bit, both the quantities are positive. Im current is positive, voltage is positive. So positive work will be done, power will be also be positive. But then it will reach maximum, then come back to 0, right? So this would be like that. Okay, power graph. And then the same thing will happen here too. Okay? And the same thing will happen here too. Okay. And the same thing will happen here too. Positive starts from 0, ends with 0, so here it's positive. But when it comes here, starts from 0 alright, becomes 0 alright. But what about this? This is positive, this is negative, so the multiplication of these two quantities will give you a negative power. So, and come here, again, this is 0 and this will also be 0. But what is happening? This is also negative, this is also negative. So, negative and negative will be positive power. And here, again, this is positive and this is positive and this is negative. So, this becomes 0. So, you see, this area will be balanced by this area, and this area will be balanced by this area. So, the net power, the net power consumed in one cycle, okay, one cycle, in one cycle, this is one cycle, right? It's going to be one cycle. One cycle, this is T. One cycle is going to be 0. So that is going to repeat. It's going to repeat, so it will always be 0. Hope this is clear to you. Let's do example problems. I'll do example 7.3 first. A lamp is connected in series with a capacitor. Predict your observations for DC and AC connections. What happens in each case if the capacitance of the capacitor is reduced? Okay, first we have a circuit. So there is a capacitor. And then you also connect a lamp to it. Okay. So this will have some resistance R. That's what I'm saying. So this is a circuit. Okay, this is lamp. This is capacitor. So what is as first you are connecting a DC power supply to this. Let's see what will happen if we do that. What is DC? I am going to connect a battery to that. That's what it is, right? So this time I am going to connect a battery. Some voltage, constant voltage V. So what will happen? The battery will start sending the current, and because there is a capacitor, it will charge the capacitor. Yeah, this current will start flowing, but then there is this charge Q that will accumulate on the capacitor, and once the charge is accumulated here, there is no way for the current to flow through it, so it will stop. This will be plus Q, this will be minus Q, so then Q by C will be equal to V. So no current will flow in the steady state. Initially, it will start flowing, maybe for a microsecond or something, maybe less than that. Immediately, as soon as the capacitor is charged, no current will flow through it. So this capacitor voltage will be equal to V, same V as this. And I, in this, after that, the steady state will be 0, no current will flow through it. For a very quick time, current will flow, will charge the capacitor, that's it, nothing else will happen. Because the current cannot flow through this, notice, like it will still charge and then it will stop. So the bulb, the lamp, will not glow. It won't even start to glow. Before even it starts to glowing, the capacitor will get charged and no current will flow through the lamp. So current should flow through the lamp, only then can the lamp glow. So no current flows through it, then the lamp will not glow if you connect DC to that. So even if you reduce the capacitance here, nothing else is going to happen. It doesn't depend on the value of the capacitance, right? The voltage across this is always dependent on the voltage you apply, because no current will finally flow through the capacitor, which means that the voltage across the capacitor must always be equal to this when you connect to DC. No current will flow. So it does not have anything to do with the value of capacitance. The value of capacitance will only determine the amount of charge you are going to have. That's all there is to it. Okay? So if the capacitance is more, then the charge will also be more. If the capacitance is less, the charge also will be less. But Q by C will always be equal to V. So reducing the capacitance will not have any impact. So even then, even if you reduce the capacitance, this lamp will not glow. This will get charged, the voltage will be equal to this, and no current will flow through this, because Kirchhoff's law will be obeyed anyway. So V plus V. No IR. Okay? V is equal to V. So the sum of the voltage across the loop will be 0. So this voltage drop will be 0, meaning there is no I in this. If I is 0, IR will be 0. So no voltage will drop across this. All the voltage will be across the capacitor. So the lamp will not glow if you connect DC to it. Okay, but let's see what happens when you replace this with an AC source. So V is equal to Vm sine omega t. So now it's AC. What does it mean? It will start from 0, it will reach a peak, come back to 0, then the voltage will become negative, okay? Then it will reach the negative peak at the valley, and it will go back to 0. That's one complete cycle. So that's what will happen. Okay. Now let's see the current will flow. First, while charging, the current will flow. Okay, it's like this. You have a capacitor, you are charging, you are starting from voltage 0, and then you start charging it. Then the capacitor will reach the voltage V, maximum. Okay, so when it reaches the maximum, then you will have Qm here, and you will have minus Qm on the other side, right? Okay, so you have charged it. But what is going to happen now? So this is the voltage. Okay, think about it. When you charge the capacitor, the voltage of the capacitor will also increase, like this. So you reach the maximum voltage across the capacitor. Now what is happening here? So as it is charging, which direction the current flows? This direction, because the charge will have to flow, right? The charge will have to flow. Now the current was flowing in this direction as it was charging. Now this voltage has reached its peak. So I'll say this is capacitor voltage. Capacitor voltage is V. Okay, and this also. Okay, I'll draw one more. Okay, this is the source V. Okay, this is V. That's capacitor voltage VC, and this is just V. Okay. So now, as this is increasing, that is also will be increasing. So you have reached the peak. So you have charging the capacitor. So you reach the peak voltage there. Now what is going to happen to this? The source. The source voltage will come down. Okay, it start reducing. If it has reached 10 volts, this will also reach 10 volts. But now notice that this is going to come to say maybe 9 volts here, something like that. But as the voltage is reducing, what is this voltage across the capacitor? The voltage across the capacitor is what? It's 10. So this is reducing. So what would this do? This will be releasing charges, discharging out. It is a higher potential, this is a lower potential, so the discharge will happen now. So the current will start flowing in this direction. I want you to understand this. As it was charging, the current was flowing in this direction. You have charged the capacitor to the maximum. Now the source is decreasing its voltage. Here it's an AC voltage, right? From peak it has to come down. So from 10 it comes down to 9. But you see, you have charged it to 10. You have more charge. It's more potential than this. So then charges will start flowing from this higher potential to lower potential. So the current will reverse direction. So current will start flowing from the capacitor to the generator, to the source. Okay, and you see the current direction is changing. Then what happens? This will keep happening till this reaches 0, right? It will reach 0, and then what happens? Then it becomes more negative. From 10, it became the source. From 10, it became 0. Now it is 0, and from 0 it is going to go negative, right? All the way to minus 10. So still it will be a higher potential, so the current will start flowing in this direction only. Okay, and from minus 10, then it will go to 0, this one. Current will flow in that direction. Then once it goes to 0, then what happens to that? Now it is going to become positive. So this potential is going to be greater than that. Now the current will start flowing in the opposite direction. So you see, the capacitor, if it was DC, you will get charged to the maximum voltage and it will stop. That's, at the applied voltage and then it will stop. But in AC, you notice that the current starts flowing from this direction to that, and from that direction to this, and again from this direction to that, because this potential at some point will be lower than this potential, but this is changing the potential. So the current will be flowing in both directions. So there will be a continuous flow of current in the case of a capacitor. okay, unlike DC. When you apply AC, continuous current will be flowing through the capacitor. Okay. So, coming back to our problem. So, what is going to happen now? So, current will continuously flow. So, if I have some capacitance C, then there is some current that will flow through this, right? The current is continuously flowing. You know that current I of t purely from capacitance point of view. I mean, that is going to be equal to Im cos omega t, something, right? Okay. It's like this. So this Im is equal to omega c Vm. Okay, this is what you got. Or this is also equal to Vm by 1 by omega c. Okay, this is not exact. It's because I also have to include the resistance in calculating the current. But then I'm trying to give you some idea. Okay, so this will do in a more perfect way when we have resistance combined with capacitance. That would come a little later. But for now, I can give you some idea. Okay, so you see, clearly, if I am going to ignore this resistance and I am going to just consider the current alone, Vm by 1 by omega c will give me the I max. And I will have some amount of current, right, at some point in time. So that is given by this expression, omega c Vm. So the current will flow. Since the current is flowing, then there will be I squared R loss here. So the lamp will glow. Okay. In the DC case, the lamp will not even glow because you charge the capacitor and then you stop. No current is flowing. But here, the current will continuously flow and the lamp will glow. Then what happens when I reduce the capacitance? If I reduce the capacitance, then what is going to happen? Look at this equation. If I reduce the capacitance to half, then you see my I max will also get reduced. If the current in the circuit is going to get reduced, then clearly the lamp will still glow, but it will glow less brightly than before because the current in it is actually lower than the current before. So this will glow less brightly. The other way of saying this, 1 by x, let's take this xc. Xc is 1 by omega c, right? So if this is reduced, then this will increase. The reactance will increase. If the reactance, the capacitive reactance, if the reactance increases, so the current will reduce, right? Reactance is like resistance, I told you. So if reactance increases, then current will decrease. Like if resistance increases for a particular voltage, the current will decrease. Likewise, if the reactance increases, the current will also, the reactance increases, the current will decrease. So you can explain that using this or using this. But effectively, the bottom line is this. When I have some capacitance, then this lamp will, and I apply an AC source, the lamp will glow. Unlike DC, the lamp will glow. But if I reduce the capacitance, the lamp will glow less brightly. Because if I reduce the capacitance, current in the circuit also reduces. And the lamp will glow less brightly than before. So that is how you do this problem. Then let's do example 7.4. A 15 microfarad capacitor is connected to a 220 volt 50 hertz source. Find the capacitive reactance and the current, in this case RMS and peak, in the circuit. If the frequency is doubled, what happens to the capacitive reactance and the current? Okay? So, let's do this. This is 7.4. So I have an AC source, and then I connect a capacitor across that. So this is C, and this is V, and that will be a current I that will be flowing through it. Okay. So what is given? The C value given is 15 microfarads, which means 15 into 10 power minus 6 farads. Okay, and is connected to a 220 volt 50 hertz source. So I told you, if they say connected to some voltage, it always means VRMS. So VRMS is equal to 220 volts, and then the frequency is given to be 50 hertz. This is typically the voltage you get at home. Okay. Then find the capacitive reactance and the current. First, what is the capacitive reactance? Set Xc is equal to 1 by omega c. Okay. So the capacitive reactance and then the inductive reactance will be calculated differently. See, XL, if you remember, XL is equal to omega c. Oh, sorry, omega L. Omega L. Then Xc is 1 by omega c. So you have to be mindful of that. Okay, what is this then? So this is going to be equal to 1 by 2 into pi 3.14. What is F? F is 50 hertz. And what is this? C, 15 into 10 power minus 6. So this is 100. 10 power minus 4 is what we'll get. And 15 into 3, it's going to be 45, somewhere around that, and 45, 48 or something like that. And when you do this calculation, then the capacitive reactance is going to be equal to 212 ohms. That's what I say. Okay. So 212 ohms is a capacitive reactance. So C is this value, so Xc is 212 ohms. Okay. Then what is the what's the current value? That's easy to get, right? So IRMS is equal to V RMS by Xc, right? Like V by R, right? So this is going to be equal to V RMS is 220 volts divided by 212 ohms. It should be 212 by 212 will be 1.04 amps is what it's given. So 1.04 amps. So that's the amount of current that is flowing through it. Let's see RMS value of the current that is flowing in the circuit. So now what is the maximum value of that current? Maximum value, you know what, right? IRMS equal to IM by root 2. So that gives you IM equal to root 2 into IRMS. You can write RMS or just write capital I. That is also the same. Okay. So that would be, this is root 2 is 1.414 into 1.04. It's roughly 1, right? So that's so many amps. That's going to be equal to, say, 1.47 is 1.47 amps. That's what I say. Say 1.4, 1.3 amps. So that is the IM. It's the maximum value. So IRMS is 1.04 amps. Then IM is 1.47 amps. So if you were to draw the graph for the current, so this is the maximum. Okay. So the current, you see, will be like this, right? So like this. This is the value of current. This I direction, T is direction. So this is V will be like that. So this is going to be. So what is this value? This is going to be 1.47 amps. That's the maximum, I max. Then it will come down to become 0, then you get minus 1.47 amps here, and then go to 0, then go to the peak again. So this is how the current is flowing in the circuit. So the maximum value is 1.47. The IRMS value for this graph is 1.04 amperes. So the root of the mean of the squared current is 1.04 amps. Okay. So that is one. So what is the second part? The second part, if the frequency is doubled, what happens to the capacitive reactance and the current? Okay. Let's suppose I'm going to double the frequency. If I double the frequency, instead of 50, I'll have 100 here. If I have 100, if I double the frequency, then what will happen to the resistance? The reactance, the capacitive reactance. If this is frequency is doubled, the capacitance will be, the reactance will be halved. So I'll have instead of 212, I'll have 106 ohms as the capacitive reactance. 106 ohms. So we have 106 ohms, then I'm going to have 2.08 amps, and this would be nearly 3 amps. Okay, so everything will double. Okay, so hope this is clear to you, and this is how we do this problem.